In this video, I want to talk about finding the average value over a planar polar region. The average value over a planar polar region involves evaluating the integral of a function and then dividing by the area of the region of integration. This is just like what we did in the Cartesian regions. The trick here is making sure we use the right area. For polar regions that involve a full circle, the area for a full rotation is given by pi a squared, where a is the length of r. If we were interested in the area of a semicircular region, our area would be half of this. Other regions of integration will require me to do a little bit more work to be sure that I have the correct area. So if I let f be continuous on a region in the xy plane defined by the set of all points r theta, such that 0 is less than or equal to r, which is less than or equal to a, and alpha is less than or equal to theta, which is less than or equal to beta, where 0 is less than beta minus alpha, which is less than or equal to 2 pi, then the average value of the function will be equal to 1 over the area of the region times the integral from alpha to beta of the integral from 0 to a of f of r theta r dr d theta. Let's work an example. I want to find the average distance between points of the disk where my set of all r theta is such that 0 is less than or equal to r, which is less than or equal to a, and the origin. So the average distance between the points on the disk and the origin over the entire disk where 0 is less than or equal to r, which is less than or equal to a. My function f of r theta is r because I want to compute the average of the distance from the origin to all of the points on the disk. My area is pi times a squared because that's the area of a full circle of radius a. So that my average value will be 1 over pi a squared times the integral from 0 to 2 pi times the integral from 0 to a of r times r dr d theta. This gives me 1 over pi a squared times the integral from 0 to 2 pi of the integral from 0 to a of r squared dr d theta. The inner integral is the integral from 0 to a of r squared dr. This is just equal to a cubed over 3. I plug that into my outer integral with the 1 over area term in front. I get 1 over pi a squared times the integral from 0 to 2 pi of a cubed over 3 d theta, which is equal to 1 over pi a squared times a cubed over 3 times theta, evaluated from 0 to 2 pi. I plug in those limits of integration and simplify my expression, and I get an average value of 2a over 3. I want to work another example. I want to compute the average value of 1 over r squared over the annulus described by the set of all points r theta such that 2 is less than or equal to r, which is less than or equal to 4. My area here is found by subtracting the area of a circle of radius 2 from the area of a circle of radius 4, so that my area is 4 squared pi minus 2 squared pi, or 12 pi. My average value of my function is given by 1 over 12 pi times the integral from 0 to 2 pi of the integral from 2 to 4 of 1 over r squared r dr d theta. I work on that innermost integral. This is the integral from 2 to 4 of 1 over r dr, which is equal to the natural log of 4 minus the natural log of 2, and that is just the natural log of 2, so that my average value of my function is given by 1 over 12 pi times the integral from 0 to 2 pi of the natural log of 2 d theta. This gives me the natural log of 2 over 12 pi times theta, evaluated from 0 to 2 pi. This reduces to the natural log of 2 over 6. Now you get to try it. Pause the video and find the average distance between points within the cardioid described by r is equal to 1 plus cosine theta. When you are ready, restart the video to check your understanding. In order to find the average distance between points within the cardioid given by r is equal to 1 plus cosine theta, I first need to compute the area. A full cardioid starts at 0 and goes to 2 pi. So I'm going to compute the area using my double integral over the region R of dA. This becomes the iterated integral from 0 to 2 pi of the integral from 0 to 1 plus cosine theta of r dr d theta. Now I want to compute the innermost integral. This is the integral from 0 to 1 plus cosine theta of r dr. That gives me r squared over 2 evaluated from 0 to 1 plus cosine theta. This gives me 1 plus cosine theta quantity squared divided by 2. I am going to rewrite this a little bit using cosine squared theta is equal to the quantity cosine 2 theta plus 1 over 2 to make it easier to compute the integral. My integrand becomes 1 plus 2 cosine theta plus cosine squared theta over 2, which equals 3/4 plus cosine theta plus cosine 2 theta over 4 after I make that substitution. Plugging that expression in for my integrand in the outer integral gives me the integral from 0 to 2 pi of the quantity 3/4 plus cosine theta plus cosine 2 theta over 4 d theta. When I integrate that, I get 3/4 theta plus sine 2 theta over 2 evaluated from 0 to 2 pi. I plug in those values and simplify, and I get 3 pi over 2 as my area for the region of integration. Now I use the area I just found to compute the average distance between the points within the cardioid. This means my average value will be 2 over 3 pi times the integral from 0 to 2 pi times the integral from 0 to 1 plus cosine theta of r times r dr d theta. Now I compute my inner integral. I get the integral from 0 to 1 plus cosine theta of r squared dr, which gives me r cubed over 3 evaluated from 0 to 1 plus cosine theta. This becomes the quantity 1 plus 3 cosine theta plus 3 cosine squared theta plus cosine cubed theta all over 3. This becomes the integrand for my outer integral, and I factor the 1/3 out front. This gives me 2 over 9 pi times the integral from 0 to 2 pi of the quantity 1 plus 3 cosine theta plus 3 cosine squared theta plus cosine cubed theta d theta. I'm going to make some substitutions in the trig functions inside my integrand, which is going to give me 2 over 9 pi times the integral from 0 to 2 pi of 5/2 plus 4 cosine theta plus 3/2 cosine 2 theta minus sine squared theta cosine theta all times d theta. I integrate that term by term, and I get 2 over 9 pi times the quantity 5/2 theta plus 4 sine theta plus 3/4 sine 2 theta minus 1/3 sine cubed theta, all evaluated from 0 to 2 pi. I plug in those limits of integration and simplify. I get 2 over 9 pi times 5 pi, which equals 10 over 9. This is the average distance between points that are inside the cardioid given by r is equal to 1 plus cosine theta. This is how I can find the average value of functions that are given to me in polar coordinates. Be sure and let me know if you have any questions.